So a few of you did izračunljivosti with me last year as a master's course. Somebody asked last week, is there going to be lots of overlap between this course and izračunljivosti, because the first lecture of izračunljivosti was also on Turing machines, which is what we covered last week. And the answer is basically no. The only overlap between this course and izračunljivosti, for those of you who took it or might take it in the future, was last week's lecture, plus the first part of today's lecture. So like the first half an hour or so of today's lecture is also going to be on Turing machines, and then we're going to move on. And while on the topic of Turing machines, I should mention that on the course web page, I've put a link to Alan Turing's 1936 paper in which he introduced the Turing machine. So it's A. Turing, it's in the Proceedings of the Royal Society. It's called On Computable Numbers. It's got a very long title, so I'll just write that, On Computable Numbers, and so on. So that's 1936. Obviously, that's a very old paper, but he wrote very well, and I recommend it as, well, firstly, historic reading, but also because it will give you, well, a glimpse into the mind of Alan Turing, which is no bad thing, but also you get a bit of a perspective about how people thought about computation in those days that was before the development of the computer. So anyway, that's strongly recommended. So the little thing I want to do with Turing machines this week, last week we did like the basic definitions and one or two examples of Turing machines. Then at the end, I went through a list of variant kinds of Turing machines and said there are many different variations you can consider, and they're all basically the same. They're all basically equivalent in power. So I just want to present one of these variants now. It's done in more detail in the notes, but just so that you've seen one of the variations on the notion, and also because we're going to actually use this variation. And for those of you who did computational complexity last year, it is also the same variation that we did there, and that's multi-tape Turing machines. And a multi-tape Turing machine, or a k-tape Turing machine, a k is a number bigger than or equal to 1. In the case it's a one-tape Turing machine, it's just the same thing that we had before. Well, if it's greater than 1, then it's a new kind of Turing machine. Well, I could give the mathematical definition, but that's given in the notes. So let's just look at it by looking at an example, and then, since we've seen definitions in one case, we can say that we've seen an example, we then understand the notion. So we're going to do an example of a two-tape Turing machine. So what does a two-tape Turing machine look like? Well, it's got two tapes. That's a two-tape machine. We're going to again have the convenience of the tapes being infinite in both directions. Various ways of doing it, but the version I'm going to consider is every tape has its own tape head. So they're all divided into squares as before, and at the start of the computation, all but finitely many of the squares are blank. So, so there are only finitely many non-blank squares. So anyway, we've got two read-write heads, one for each tape. And once again, the tape has a control space, the machine has a control space. And as usual, it starts in the state start. And as usual, to run the machine, we'll run it on some input. Now, there are various ways of using a multi-tape machine for input. For example, one nice thing you can do in a convenient way with a multi-tape machine is you can compute functions in 2 or more arguments. like from a product space by giving each separate argument on a separate tape. You can also, it's often useful to use additional tapes as working tapes, even if you've only got a single input. So I'm going to consider an example where we have a single input. In this case, I'm again going to use an input alphabet AB, and it might be the same input word as last week, I don't know, it doesn't really matter. So this particular input word is ABA, and what I want to show you is how the machine runs and what the instructions look like. Now, once again, the instructions are given by transition partial function, and as before, they tell us what to do from a given configuration. Let's see, I want quite a lot of space here, so let's, I'll just write small, but hopefully you can still read it. So if we're in start, as we are, and we can see, so now on the left-hand side, we've got two tapes, so we've got two bits of input from the tape heads, namely what we can, the character we can see here, the character we can see there. And in this particular configuration, we can see an A on the first tape and a blank on the second tape. And in that case, we have an instruction that tells us what to do. In that case, we stay in the start state. We keep the A on the first tape. We write an A on the second tape, so keep the A on the first tape. We write an A on the second tape. And I'll stop writing the pluses. We move one to the right, that was a +1 last week on the first tape, and one to the left on the second tape. I haven't actually written that second instruction down, the one to the left. So that's what it looks like. So here we have a 3 tuple for a 2-tape machine. We have a k-tape machine, we have a k+1 tuple where the first component is a state, and the other components are symbols from the tape alphabet. Here we have a 2 times k + 1 tuple, where the first component is again a state, the next k tuple of components are symbols from the tape alphabet, and the final k tuple are direction, are displacement, so -1, 0, 1, relating with the tape. Okay, we're now looking at B and a blank. So remember in start, you can see a B and a blank, and we go to stay in start. We keep the B on the first tape, we write a B on the second tape, and again we move one to the right on the first tape and one to the left on the second tape. So we've written a B here, we've kept the other B, moved left on the second tape and right on the first tape, still in the start state. We're now again in the state in a configuration where we see an A and a blank. So we keep the A, we write the A here, we move the head here right, we stay in the start state, and we move the head here left. And now we're in a new kind of configuration where we see a blank on both tapes. In that case, so when we have a blank, I should say, so there are the lecture notes, the LaTeX lecture notes that you've got access to off the course webpage. They're growing through the course, so every week there'll be another chapter added, namely the chapter for this week's lecture. The lecture notes basically have all the material with more details, except pictures are annoying to do in LaTeX, and obviously I could, so they don't have the pictures. So when the picture stuff in the lecture, that's supplementing what's in the lecture. Anyway, so if you've got 2 blanks, you go to a new state called back, keep the blanks on the tapes, and we keep the tape head in the same position on the first tape, and we start moving to the right on the second tape. So here, we're in start with 2 blanks, so we now change to a back state. We keep the 2 blanks, we keep this head where it is, and we move this head 1 to the right. Okay, we now need to know what we do in back state. So here we're in a back where we see a blank on the first tape and an A on the second tape. In the back state, so you're blank on the first state and an A on the second state. You stay in the back. We keep the blank. We keep the A. We keep the first tape head where it is, and we move the second tape head one to the right. So staying back, keep the symbols, keep this head where it is, and move this one to the right. Similarly, if we're in back, we've got a blank on the first tape and B on the second tape. We stay in the back state. We keep the blank, we keep a B, we keep the B, we keep the first tape head where it is, and we move the second tape head to the right. So this tape head just goes there. We're now in back, we've got a blank and an A. We've already seen what we do there. Everything stays the same except this tape head moves to the right. And now we're in a new kind of configuration where we're back and we've got two blanks. And if we move back, we've got two blanks. We go to a new kind of state match. We keep the blanks and we move both tape heads to the right. Okay, so we go to match here. Keep the blanks and we move both tape heads to the back. The point of the match is to check that you've got the same symbol on both tapes where the heads are. So if we're in match and we see A's on both tapes, we're happy. So that means we keep in the state match. Doesn't really matter so much what we do, but it's nice to tidy up in a nice way. So I'm going to keep the A on the first tape, write a blank on the second tape, and move both tape heads to the left. So we stay in match. We keep the A on the first tape, we write a blank on the second tape, and we move both tape heads to the left. We're in match and we see two B's. So again, it's the same symbol on both tapes, so we stay happy. And it's similar to the A instruction, so we stay in match, keep the B on the first tape, write a blank on the second tape, move left on both tapes. Here again, we're in match and we're seeing two A's. So just as we did before, sorry, I should have, that B got erased on the previous move. But just as before, we keep the A on the first tape, we erase the A on the second tape, we move left. Now we're in match and we see two blanks. In that case, we go into the accept state and we keep the blanks, we keep the second tape head where it is. Second tape head, the first tape head will move on to the right. Okay, so we go to here, go to accept. Of course, accept is a halting state. We always want to accept the halting state. That's almost a complete machine, but I didn't tell you what match would have done if it had got to a state in which it found two different symbols on this tape. And in that case, we could do that we could encounter that in two ways with this alphabet. We could either have A on the first tape and B on the second tape, or we could be in match and see B on the first tape and A on the second tape. And in that case, we go into reject state. So let's just keep that information we've got. Really matter what we do. Okay. And that's the machine. So the word ABA got accepted. So as you remember, last week we had the notion of a language. Or maybe just to finish it. So this was sigma this two-tape machine has this for its input alphabet. Its tape alphabet, as we can see, is A, B, blank. and the set of states it has, so to specify it, we would give this transition partial function, the tape alphabet, and the set of states, which is start, back, match, accept, reject. Last week we had the notion of a language, which is a set of words over the input alphabet. So remember, this means settable sequences or settable words over the alphabet 0, 1, and the language is just a subset of the set of words. So it's a set, subset of words. We had the Turing machine M besides L. If we run M on W belonging to L, then it goes into an accept it. So this was done in more detail last week, but this curly arrow here means it eventually halts in an accept state. If we run M on a W that's in the input, it's a word over the input alphabet, but I'm going to use this for the set, just a minus for the set difference operations. People sometimes use a backslash. If you're running on a word outside the alphabet, outside the language, the machine halts in the reject state. So a machine decides the language if it gives us, for words in the language it says accept, and for words outside the language it says reject. It gives us good information, and we had the weaker notion of semi-decides language. If again, it will accept any word that belongs to the language. So again, I'm writing in a brief way, but we run the Turing machine M on a word in the language, and eventually that computation goes into the accept state. And if we run M on a word that's outside the language, so from the input alphabet but outside the alphabet, then the machine, the execution of the machine on that input execution does not end in the accept state. It doesn't need to. So whereas deciding it needs to end in the reject state, we get this kind of positive information that we're rejecting the word. In the case of semi-deciding, all we require is that the machine doesn't go into the accept state. It might accept in some, it might terminate in some other state, or it might go into a loop. So given these definitions from last week, what can we say about this particular machine? What language does it decide a language or semi-decide a language? And if so, which language?
Decides the language of palindromes.
Right, exactly. So there's the language of palindromes, those words that read the same forwards or backwards. If you read them forwards, it's the same as reading them backwards. And this language decides that, machine decides that language. You give it a palindrome, it accepts it. That was the example we saw. You give it a word that's not a palindrome, it rejects it. It goes into the reject state. Okay, so let's just write that in this little blank space here, bless you. So this machine decides the language of palindromes. This is a nice example for a multi-tape machine, because you can write a single tape Turing machine that will decide the language of palindromes, but the time that the single tape machine takes to decide the language of palindromes is necessarily quadratic in the length of the input word. Whereas this machine here, this two-tape machine, the time it takes is linear in the length of the input word, because it just scans the word once, then moves, heads back, and then scans again, both simultaneously. So it basically does 3 scans of the length of the word. So it's linear time in the in the length of the input word. So we see from that in a sense, multi-tape machines are more powerful than single-tape machines because they're faster. So this is a faster machine for deciding the language of anagrams. But in this course, this is where computability theory diverges from computational complexity. Computational complexity is all about the time and space that computations take. In this course, we're going to be more concerned just about whether or not we can compute something irrespective of time and space. And we're going to now see, very briefly, that if we neglect worrying about time and space, then multi-tape machines are no more powerful than single-tape machines. And to do that, it's obvious that a multi-tape machine is at least as powerful as a single-tape machine because a single-tape machine is a special case. But basically, even if you fix the number, then it's no longer a special case. If you fix the number of 15 tapes, then single-tape machine is no longer a special case, but you've clearly just got more to work with on the multi-tape machine. So it's clear that multi-tape machines are more powerful. So how do we go back and show that if we can compute something? So let's look at, say, deciding a language. Suppose we can decide a language on a multi-tape machine. How do we know we can also find a slightly more inefficient, but nonetheless a single-tape machine that decides the same language? And the way this works is we show how on a single-tape machine we can simulate the execution of a multi-tape machine. So let's move the camera. So a single tape machine can simulate a K tape machine for any fixed K. So, given the K tape machine with some tape alphabet, gamma and Q set of states, I shall wait. Is there a question? Is there a question? No. Very American accent. Okay, so if you've got a K-tape machine, specified by tape alphabet states, and the transition function, which has the right length of tuples in it to specify the K-tape machine, you simulate it by a single tape machine. In the following way, we basically code up configurations of the K-tape machine using the single tape machine. So I think, as I said, there are details in the lecture notes. In fact, in last week's lecture notes, in the first chapter of the PDF. But for the purposes of the lecture, I think it's just better just to see things visually. So let's just have a picture. So suppose we want to simulate the execution of a two-tape machine. Two is a convenient K, for example, because don't need to write too much. So we've got two tapes, and we're in some state, some configuration rather. The difference between the configuration and the state is the configuration is the whole contents of the tapes plus the control state that you're in. So it's better to reserve the state just for the word state just for the control state. So for example, we might have A, B here, just for example, some tape head here. And maybe we're in we're in the configuration, and on the second tape perhaps we've got PBA, maybe the tape head's to the right here. And we're in some state Q. So we simulate that so this is the, and it's obvious because it's got two tapes, that this is the two tape machine. It's a configuration of it. We want to simulate that using a single tape machine. And the point is, every configuration of the two tape machine we translate to a configuration of the one step of the single state machine. Then every single step between configurations on the two tape machine, we translate to some process on the one tape machine. The one tape machine is going to be slower, so it can't do it in a single step, but it can do it in some finite number of steps. It can go from it's encoding this first configuration to encoding the second configuration. So we want to put this two tape configuration on the single tape. There are many different ways of doing it. The one that I like is this, that we use a special symbol to say we're starting encoding a tape. So this is like a double bar symbol. We then encode so remember this tape is necessarily non-blank only on the finite. It's blank everywhere except on the finite portion, so there's just a finite portion on which it's non-blank. You then take the non-blank portion here and write it here. So this is going to be the first tape. But we also need a symbol for the tape head to say where the tape head of this tape is, because on the single tape machine, we're only going to have one tape head. So rather than, in order to encode where the tape heads are on the two tapes here, we have a symbol in the tape alphabet on the one tape machine that tells us. So here we have the symbol for the tape head, and this says, I am pointing at the character to my right. And the character to my right is A, and then B, and that's the end of where the word is on there. So now we can put the separator symbol. This says, now we're going to start the encoding of the next tape. The next tape is B, A, and the tape head's actually pointing into blank. So we need to put the tape head in, and let's put a blank in as well. Okay, so that encodes the two tapes there. And then we need state Q. We could use Q again, but I mean, because we're going to take many different steps here to make a single step of computation here, I prefer to have a state here called now Q. And that's basically saying when we're in this state, we're saying this one tape machine is capturing at this point this configuration of the two tape machine. And when we're in now Q, I always want the single head that we've got for the one tape machine to be at the left of the encoding string. Okay, so this is my encoding of the configuration Q. So we simulated by a single tape machine using tape alphabet. And the twiddles in the single tape machine, which is just simply the original tape alphabet together with the two special symbols for the one that marks the division between the tapes, and the symbol that stands for the tape heads of the multi-tape machine. And states Q, which is going to be a superset of states, so it's going to include the state now have a little cube for every control state little cube of the original machine. I'm making this a superset, because we're going to need lots of other control states, because we're going to, in order to make one move of computation here, we're going to need to use several moves of computation here, and we're going to need quite a lot of other control states to be able to do the multi-step of computation. I'm not going to give them, no. It's a nice thing to think about how to do this. But I don't want to take up a lot of lecture time on it. And we have a new transition function, which is quite complicated, so I'm not going to write that at all. I'll just call it delta twiddles. But I just want to say how it works. So we want to simulate the computation here. So basically, the way it works is we look at which instruction applies here. So maybe it will say, well, we're looking at rule A, we're looking at a blank on the second tape, and we want to replace those with a certain character, and we want to move this one to the left and this one to the right, or something like that. So this one, we need a machine here that says to this one, scan through the information we've got. In fact, let's do it this way. We're going to scan and return to here. We're going to scan through and first look at all the places of the read head of the heads on the individual tapes up here to see if we've got an A and a blank, because we're trying to do the instruction for an A and a blank. So we'll scan through, we'll pick up what this head's pointing at, which is little a, what this head's pointing at, which is little blank. Then, with that information, go back to the beginning in a suitable state, not one of these now Q states, but one of the other states we're going to need that says, okay, replace this with well, this head's pointing at with a B, say, replace what this one's pointing at with a blank, move this one to the left and move this one to the right.
So when you say store the information, you mean like a bunch of states?
So we've got a bunch of states, one for each of those possibilities, but there are only finitely many such possibilities of things we can be telling it to do. So the actual definition of the machine is quite complicated. But indeed, so that's all that information is in the state when we get back to the left here. We then scan through to the right because we're in that state. We know what to do when we get to this, and we know what to do when we get to this. Something that's very awkward is if we needed to move this head to the left, we would have to create some space. If we needed to move, well, this eventually to the right, we would have to create some space because we have to expand the representation here. But you can do that. You can write on a single tape Turing machine something that takes a word like this and inserts as much space as you want in this position. Anyway, the basic idea is encode the information in the states and scan the tape enough times that you can basically carry out the computation in quite a lot of steps. All that's just for a single step of computation. And then eventually you get back to the beginning there and you go into now Q of prime, where Q prime is the next state that this machine is going to. Right, oh, very good. Any questions about that? I don't think I want to go into any more detail. Okay, so we've got here what it means for a Turing machine to decide a language, what it means for a Turing machine to semi-decide a language. You may remember from last week, I'm not going to rewrite these up, but a language is decidable if there exists a Turing machine that does not decide the language. Sorry. It's decidable if there exists a Turing machine that decides the language. And it's semi-decidable if there exists a Turing machine that semi-decides the language. Every decidable language is a fortiori semi-decidable. that means for a stronger reason, it's semi-decidable, because being semi-decidable is a weaker property than being decidable. So every decidable language is semi-decidable. But at this point in the course, I mean, I'm sure almost all of you know, but at this point in the course, it could be the case that every language whatsoever, every set of words is decidable and semi-decidable, so we wouldn't need to have the distinction. So do there exist languages that are not decidable? That is, do there exist undecidable languages? The language is undecidable if it's not decidable. Just the word undecidable means the negation of decidable. And other languages that are not even semi-decidable. Of course, the answer is yes, and this was kind of Turing's big contribution, but I want to just end this first hour with a very quick proof that there exist languages that are not semi-decidable, and hence languages that are not decidable. And that proof is the following. To specify a Turing machine, we give a finite amount of information. We give a tape alphabet, a finite set of states, and a finite transition function. Maybe if we talk about Turing machines that decide the language, there's a little bit more information, which is also the sigma, the capital sigma, which is the input alphabet, but that's still a finite amount of information. And because you're only giving a finite amount of information, there are essentially only a countably infinite number of ways you can give a finite amount of information. You can enumerate all you can count through all possible Turing machines using natural numbers. There are countably many Turing machines, basically, up to equivalence, where if you're saying, well, we could have the set, we could use any real number as a state, then you get into nasty territory, but it doesn't matter what we call symbols. It doesn't matter what we call the states, we could rename them. So allowing ourselves to consider two Turing machines as equivalent, if we rename them, there are only countably many Turing machines. And any Turing machine semi-decides exactly one language, namely those input words for which it goes into the accept state. So there are countably, there's an countable infinity, countably many Turing machines. Every Tn semi-decides one language. Therefore, there's a countable infinity of semi-decidable languages. There are countably many semi-decidable languages. But so everyone that remembers logic from first year undergraduate will remember. I mean, other people have done more advanced courses on similar things, but there are uncountably many languages. Because for any non-empty alphabet, and we're only interested in non-empty alphabets, because the power set, so a language is a subset of words over an alphabet. There are countably infinitely many distinct words. You can enumerate the set of words. And so this is the power set of a countable set, and that's by Cantor's theorem from logic in Logitza, basic set theory. This is an uncountable set. There are uncountably many languages. This is the set of all languages. As cardinality the continuum. So there are clearly because only countably many of them are semi-decidable, there are a lot of languages left over, so there are clearly uncountably many languages that are not semi-decidable. In conclusion, there exist uncountably many languages just to make one comment about this, so I know that half the course is Isher and Ma. There are also some financial maths students here. So like half the course didn't do logic in Nojica, and maybe half the course don't know about countability and uncountability of infinite sets. So if this was too abstract and weird for you, it doesn't matter, because from the next part of the lecture, we're going to see an explicit construction of languages that are not decidable, and so this is an abstract proof, but we're going to see something more interesting, and you don't need to worry too much about this abstract proof. Okay, any questions?
We're looking this over a fixed alphabet and everything.
Yeah, so over a fixed input alphabet. Yes. Yeah, otherwise you get the problem that you could pick any pair of real numbers for your alphabet or something like that, and then there are a multitude of languages just because you can change the symbol.
Yeah, but also you have uncountably many sets of possible alphabets in the first place.
Yeah, no, exactly. No, that's exactly the point. Yeah, that's what I meant. Sorry. Yeah. Okay. Other questions? Good. So we'll pause the video and yeah, so it's basically 3 o'clock, so we'll start again at 1:15. Okay, so right at the end last time we had abstract proof. Have an abstract proof. That there exist languages that are not semi-decidable, and there exist languages that are not decidable. That there exist undecidable languages. By the way, just I'm not going to make remarks like this very much, but in English it should say we have an abstract proof that there exist undecidable languages. And I kind of feel that I ought to feel morally obliged to put in all articles, because articles in English are something that Slovenes struggle with, because you don't have articles in Slovene. But when writing on the board, it's just very annoying to put in all articles. So whiteboard written English is also potentially Article 3, at least when I do it. I apologise for that. I will always put the articles in when I speak. It's most of the time. Anyway, we have an abstract proof that there exist undecidable languages, but what we're going to do the rest of today is something more interesting than just an abstract proof. We don't actually have a specific example, so we're going to give a specific example. So we shall, so the rest of today, an explicit example of a language that is undecidable, language. And also a proof that this language is semi-decidable. But this particular example is semi-decidable. So that's good, because it then shows us that there is actually a difference between decidability, being able to computationally give both a yes answer in the case that a word's in the language and a no answer in the case that the word's not in the language, So that is a different concept from semi-decidability, in which one only requires the yes answer, but you don't require the no. Okay. So this is going to be the next hour, and the last part is going to be the third hour of the lecture. The way it's going to work is these languages are going to encode properties of Turing machines. So actually, our language is going to be a collection of words that say something about Turing machines. And in order to achieve that, we need to encode Turing machines as words. So that's the first step. And let's go to a clean board for that. We're going to have encoding Turing machines as words. Now we've seen that that multi-tape machines are essentially equivalent to single-tape machines. So the kind of philosophy of how we're going to work with Turing machines is this: when we need to manipulate a Turing machine in some way, like encode it as a word or something, we'll use a single tape machine because it has the least amount of information there to deal with. But if we want to give some computational procedure by giving a Turing machine that's going to do it, we're going to use a multi-tape machine because then we have as much power as possible to facilitate being able to do it. But we know that the two formalisms are equivalent, so we don't need to worry about switching between the two. In this case, we want to encode something as words, we want to capture all the information regarding the Turing machine as a word. So we're going to use single tape machines to have the smallest amount of information to encode. So we will encode, so to encode the Turing machine of the form gamma, that's the tape alphabet, Q, set of states, and delta. And we're going to encode it over, we're going to encode such a Turing machine as a word over an alphabet. Let's call this N, it's Turing machine. So we give this an encoding. I'm going to use angle brackets for the encoding. So angle brackets add means the encoding, and it's going to be encoded as a word over a particular alphabet, sigma u, where u stands for the universal alphabet. So this is going to be a word over the alphabet sigma u, where sigma u, basically, it could be 0, 1, because actually in practice, in the real world, when we encode anything, we encode it on a computer and it gets translated into binary. But if we made sigma u just the language of bits, then the encoding would look messy. So we're going to give ourselves as many symbols as are convenient for doing it in a readable way. And what I find convenient is to have 0, 1, and -1. Some square brackets. So we have the opening and closing square brackets. This double bar symbol. It could be a single bar, but it's kind of easier to read if it's a double bar, and a bullet. Magic bullet. So we've got 1, 2, 3, 4, 5, 6, 7 characters in our alphabet. We're going to code as a word over that. And we're going to do that by breaking down the different components. So first we've got the states. So for every we encode every control state, little q, in the control space of the machine as a word. So for control states, again, we use angle brackets to say we're encoding the state. And the control state, we're going to encode using just the 3 numbers 0, -1, 1. And all control states are going to, just for convenience, be encoded as strings of the same length. So we're going to give them some, that's a maybe looks like an E, but it's an L. So we're going to encode them some length L, where L is just a chosen number. Well, what do we require of L in order to be able to do this? Well, we have this many control states. This is the cardinality of such control states, the number of control states. In order to be able to encode every control state as a distinct string of length L, how long do we need L to be? At least what? Okay. Log sub 3 of length of Q. Very good. Log to the base 3. So here I've got ceiling in my notes, but actually it's irrelevant because if L is going to be an integer anyway. So so that's because but we have some particular states already, so we're going to require a machine. We're going to look at machines that are accepting, or machines for recognizing languages. So they have a start state, an accept state, and a reject state. So we're actually going to require for our encoding that those are represented in a canonical way. So we require that the encoding of start is this means the word consisting of L zeros in sequence, except it's going to be one L1s in sequence, and reject is going to be, I'm going to write it like that, L minus 1 sequence. Okay. Okay, so that's the states. We need to encode the alphabet. So we're going to encode every symbol in the tape alphabet. In the tape alphabet of the original machine as, again, a word angle. So again, it's encoded. So again, we use angle brackets. And again, we're going to use only the symbols -1, 0, and 1. The point of this is that we're going to use these symbols for data and the other symbols as kind of punctuation marks. They look like punctuation marks, but just for separating things nicely out. So here we'll use M for the number there. And of course, in this case, the sum chosen M. So M now needs to be greater than log base 3 of number, the size of the tape alphabet of the original Turing machine. And of course, we've got a special symbol in the tape alphabet. What is it? The blank. So let's encode blank as the constant sequence of zeros. So we require that the encoding of blank is 0 to the M. Okay, so we've already encoded the gamma and the Q. So we've only got the delta left to deal with. Of course, that's the complicated part of the Turing machine, what the transition function is. Let's do that. And this is where we're going to use a lot of the punctuation. All of it, in fact. Stop really in the middle. I need to move the camera. So for every instruction, so we can view the transition function as given by a list of instructions, as we have been doing. So for every instruction delta of the form from, whoops, let's not make the A look like the Q, from state control state Q and looking at symbol little a, we go to control state Q prime with the new with symbol B over written where the A was, and we go and we move the tape head with this displacement, -1, 0, or +1. So here we have Q and Q prime are in Q, A and B are in gamma, and D is in -1, 0, and 1. So we encode this as the word. The word. So I use square brackets to say it's the start of an instruction. We put the encoding of the state Q. Use the bullet here. So the point of the bullet is to separate things out. So this is in separating it out from the encoding of the symbol A. We then use this double bar as to say we're ending this pair part, and then here we simply put the encoding of Q prime, the encoding of B, and D itself is -1, 0, or 1, so we can do it simply. We have those in the alphabet already, so we don't need to encode anything. Just put D itself in. So this has length. Somebody work out the length. Right, so that is it's not really worth waiting for an answer because it's obviously an easy exercise. It's 2L plus 2M plus 7. Okay, so now that's a single instruction. So how do we encode the whole transition function? Well, just the transition function is just a collection of such instructions. So that's not going to be a problem. We'll just move straight away to encoding the whole Turing machine. And the encoding of the Turing machine is now defined as M is the encoding of the Turing machine M is as follows. We start with the encoding of start, which is some number of zeros. And the reason for this, you don't need to do this. It's just when we're going to write something called the universal Turing machine, which is in the next hour, not this hour, it's actually very convenient to have an encoding of a state here, just so you can read a number of L's and from it get M. So you can read the number, so you know what your length of encoding is. This allows us to know what our length of encoding of the state is. And for the same reason, we follow it by the encoding of a blank, which tells us how many symbols we're using to encode symbols from the tape alphabet. And having done this, we simply follow with encodings. Suppose the transition partial function has k different such instructions in it. So it's defined on k different pairs. We simply include the encoding for k of these. So the first one would be the encoding of the first instruction, so that can look like this: A1, 1 prime, Q, E1, E1, all the way through to the encoding of the kth instruction, so QK, AK, double bars, U1 prime, so QK prime, BK, EK. I mean, I could say, I could write out where delta is this function that maps these k pair tuples in each of these ways. I'm not going to do that on the board, but you can, there's a more formal treatment again in the notes, but hopefully this is enough to be able to follow what's going on. Okay, so this is how we encode a Turing machine. We say how many symbols we're using to encode states, how many symbols we're using to encode characters in the tape alphabet, and then for each instruction in the transition function, we encode the instruction in a very simple way. One other thing we need to do is encode words over the tape alphabet of the Turing machine. So we encode any word W over the tape alphabet of the Turing machine as, well, simply this. So suppose we write this word W as, so one of the most annoying decisions I made in writing the notes for this course over a few years was this question, which is kind of the question that decides whether you're a computer scientist or a mathematician, which is whether you start counting with 0 or whether you start counting with 1. And in the end, for some reason, I went for the computer science choice, which is to start counting with 0. I always regret it. But anyway, this is a word of length n. So a word of length n we're going to write as W0. That's the first character, followed by W1, that's the second character, all the way up to W. The annoying thing is you always have to write an n-1 in here. Anyway, very occasionally it pays off to have a 0. Not often enough. But nonetheless, the notes are written like that, and I don't want to rewrite them. In any case, so to encode a word, well, what do we do? Well, we simply encode each of the symbols of the word, each of the characters in the word, and we don't need to separate them because we know what the lengths are, but just it's easier to write the Turing machines that manipulate these things if you do put some punctuation in. So we are going to separate the encodings into characters so you can see where the characters finish. So -1. Okay. Now we already have all the machinery we need to define our undecidable language. So, well, that's the language of interest. You like it, this is now we're finally meeting the main character in today's lecture. That's this language. So we call L accept. Protagonist, if you like. So L accept is defined to be, it's going to be a language. So it's a collection, it's going to be a language over the alphabet sigma u. So it's going to be a collection of words, a set of words of these symbols. And it consists of those words of the form, words that arise as an encoding of a Turing machine, followed by a bullet, followed by an encoding of a word W. So where M is a single tape Turing machine with, and it's very convenient to only consider those Turing machines whose tape alphabet contains sigma u with tape. But any Turing machine can be considered as such a Turing machine because any Turing machine is always a Turing machine over a larger tape alphabet. It just maybe doesn't use the additional characters in the alphabet. We're going to consider any Turing machine as being over tape alphabet gamma that contains this alphabet sigma u. W, we want that because we want W to be a word over sigma u. So W belongs is a word over the alphabet sigma u, so a member of the set of words over the alphabet u. And importantly, M accepts W. If you run M on input W, then the computation terminates and it terminates the accept state. Okay, so that is a perfectly legitimate language. It's quite hard to describe in the sense that it requires the knowledge of what a Turing machine is and all this encoding of Turing machines. And this language is going to prove it's undecidable and that it's semi-decidable. And we can just go straight away and prove that it's undecidable. So that's what we're going to do. To prove that it's semi-decidable requires a lot more work. But decidability is quite straightforward. I mean, the proof's a clever proof. It's a sort of diagonalization proof for those who've met diagonalization proofs. But I'm not going to spend time today to talk about its relationship to diagonalization. But those who've met proofs by diagonalization before probably recognize some routines. So that's something to bear in mind, not like think about eventually, but I'm just going to give it as a self-contained proof anyway. So we'll state a theorem and we'll prove it. Theorem. This language L accept. Obviously, it's called accept because it's about the input is essentially coded up a Turing machine in a word. The language is those Turing machine word pairs that where M accepts the word. So L accept is undecidable. Okay. Now, it's kind of proof that my past experience, I know I should have my notes in front of me because otherwise I tend to go off on autopilot and something goes wrong somewhere along the way. But we're going to prove that L accept is undecidable. So what do we want to do? Well, we're going to assume it's decidable and get a contradiction. So proof, I suppose, so in English mathematics, one often writes a hash for contradiction. Okay. That so this means supposed to contradiction that L accept. Decidable. Well, what does that mean? If it's decidable, then we have, by definition, a Turing machine N that decides the language. Oh, sorry, D. I'll stick to the notation in the notes. So there exists a Turing machine D that decides how to accept. Okay. Now the Turing machine N is going to come in because what we're going to do is we're going to use D to define a new Turing machine. The fact that we have a machine D, we're going to manipulate this machine a bit to define a new Turing machine, which we'll call N. And the point is that Turing machine N is going to be able to prove that it's self-contradictory that such a Turing machine exists. So we're going to use D to define a new Turing machine N with input alphabet sigma U. And this machine N works as follows. So N reads its input string. Okay, so now we're defining a Turing machine. One can be very formal and say, okay, from this Turing machine D, we have a transition function, and we're going to use that transition function to manufacture a new transition function for a different Turing machine N in the following explicit way, but that would be totally unreadable if we did it like that. It'd be very hard to follow. It's much easier to just say what the algorithm is that N is going to follow and leave it as an exercise, a fun exercise, and all these cases that involve defining Turing machines. It's quite fun to try to do it yourself, to actually write down this algorithm in terms of the transition function Turing machine. But informally, N reads its input string, input string B, I use string and word interchangeably, by the way, and converts it. This is the first clever bit it does, converts it to the string V followed by the encoding V. So it's easy for it to output V as the first part, it just copies its input, then it puts a bullet there, but then it needs to put the encoding of V there, so it needs to go through every symbol of V and put its, the encoding of a word that's defined here, so it goes through every symbol and puts its encoding there. This, clearly you can do that with finite computation, because each symbol has a finite encoding, and you simply do that and you get lots of things separated by bullet points, by bullets. Okay, and now once n has done that, so it's now got a new string there. So it now proceeds as D from this input. So n now proceeds as D. So basically now n just carries on as D would carry on from this input, except for one thing, which is when it gets to the end, it inverts the accept and reject states. So if D were going to accept this, n will reject it. And if D were going to reject this, n will accept it. Except that at the end of the computation, so if D halts in accept on input V followed by encoding to V, then n halts in reject. And conversely, if D halts in reject, then n halts in accept. Okay. So we're going to consider. So maybe some of you can already see that there's a contradiction going to arise out of this. But to bring it into plainer view, I want to do the following, which is consider what the Turing machine n does when given an input string of a certain form. So let's understand the behavior of n in more detail. Let's consider what n does when given an input of the form the encoding of a Turing machine n. We'll call this V. So here, so I mean, if you input to the form the encoding of a Turing machine n, and I'm defining that to be V. Okay? Or some VM, some Turing machine n. So in this case, it gets a bit complicated. So then n proceeds as D on the input. So n proceeds as D on this, it converts it, the input is given to this, that proceeds as D on the input that we take this input string and follow it by its encoding. So we get quite a lot of angle brackets coming in. We get the encoding of the Turing machine n, that's a word over sigma u, followed by the encoding of that word as a word over -1, 0, and 1. Well, no, there's some bullets. So the encoding of that word. So we get like lots of little brackets there. And it terminates, and then terminates in accept if D rejects, and it terminates in reject if D accepts. So because D decides I'll accept, because D decides I'll accept, we get from N the result state except if and only if, well, if and only if the input to D is not, so except if and only if D rejects, which means if and only if the input to D is not in L accept. So if and only if encoding of N followed by encoding of N is not in L accept, and we get reject if and only if that string that we're giving as the input to D is in L accept. But by the definition of L accept, this is if and only if M accepts. So this is not in L accept, but this is only if M is not. Sorry. So it does not belong to L accept. Oh, so, okay, so yeah. So this is if M. So this belongs to L accept by the definition of L accept if and only if M accepts the input M, and if you don't belong to M accept, it's the opposite of this, so it's M does not accept input M. So this is what N does if we run it on the encoding of an arbitrary Turing machine. Yes?
You wrote does not accept. It could be maybe this means rejects, right? Because
no, rejects means halts in a reject. Yes, actually.
Yeah, but
it means does not accept.
Okay.
Because this is just N's an arbitrary machine here. Oh, okay. We're just considering what we do. We're considering what happens if we run N on the encoding of an arbitrary Turing machine. And for an arbitrary Turing machine, the language is defined to be those pairs for which N accepts. So if a pair is not in the language, it simply means N does not accept that input. No more than that. It might not reject it. But maybe you're just jumping one step ahead, because now we're going to consider what N does if we give it its own encoding as its input. And in that case, N is a Turing machine which is guaranteed to accept or reject because, by the way we've defined it, because D is guaranteed to accept or reject the decision procedure. So consider what happens if we run, and I think I really need some more space. Sadly, it won't quite fit at the bottom there. It's always the slightly annoying thing of, I'll tell you what, I can use the right-hand column here. That's already in the video. So consider running, what happens if we run the Turing machine N on its own encoding. So then we get, for the computation, we get except if and only if by this N does not accept not accept. It's only input, it's only encoding, in which case, by the definition of n, it does reject it because we've defined n in such a way that it will always accept or reject. But actually, that fact doesn't need to come into the argument. And we have the running n on n reject if and only if n accepts. It's encoded as input. But this is a clear contradiction because we're saying running n on n does this if and only if it does the opposite, and vice versa. Yeah. So both alternatives are absurd. Both cases are absurd. We only need one of them to get a contradiction. Hence, well, where did we make an assumption? Only at the start. So that assumption was clearly wrong. So hence, L accept is undecidable. Okay, so we now have a nice explicit description of an undecidable language. Right, it's 5 minutes early. I'll see if there are any questions, but this is actually a good stopping point, so we'll break at this point. But are there any questions?
Soft one.
Yeah, a soft question, they're the best question.
I mean, this is the whole thing here, fingers on the fact that we can feed and its own
Yes.
encoding, right?
Yeah.
But I mean, I'm thinking with the parallels of lambda calculus, where in untyped lambda calculus, you can, apply a function itself.
Yeah.
But there you have typed lambda calculus, which doesn't allow for such a thing because, I mean, you can't feed a lambda from into itself because you can't get that really well typed. So,
well, unless you have something called recursive types. You can have types that do allow it, special kinds of types that do allow it.
with a sufficiently rich type system.
Yeah. So in fact, there are the kind of type systems that are used in formalisms for formal reasoning, for example, like the sort of what's in loft type theory and so on. Yeah. These tend to have the property that if you review them as programs, they will terminate.
Okay.
Yeah.
So,
but if you add some fancier kinds of types, then called recursive types, then they no longer will terminate and index issues like this. So the people that choose lambda calculus as the presentations on the 6th of November are all about models of computation. One of them is going to be lambda calculus, and the people that choose lambda calculus can tell us about this sort of thing. Maybe not the types, but certainly about applying functions to themselves and defining things called fixed point operators.
I mean, can you do something like the Y combinator?
Yes. Okay. So you can't do so. The Y combinator is a famous thing in lambda calculus that allows we do general recursion. It's called the fixed point combinator. We can't define it in type systems that people use for formal reasoning where everything terminates, but in fancier type systems, a little bit more closely aligned to some sorts of programming languages, you can define it. So a nice thing to learn about. Good. Any other questions? Soft or hard? Or in between? Okay, good. Well, it's still 2 minutes early, so we'll start again at 13 minutes past. Right, so the main remaining goal of today's lecture is to prove that this language L accept of pairs of encodings of Turing machines and words of those pairs such that the Turing machine accepts that word, which we've proven to be undecidable, to show that it is semi-decidable. But to prove that it's semi-decidable, we need a significant tool, and that tool is not just a tool for this, but a very useful tool for many things in immutability theory. And it was one of the major contributions of Turing's paper on Turing machines, the undecidable on computable numbers, etc., etc. And this Turing machine is what this contribution is, it's very famous. It's a special Turing machine that exists. It's called the universal Turing machine. So this is something that I'm going to describe what it does as a theorem. So the theorem is there exists a machine, the universal machine, that behaves in a certain way. That theorem doesn't tell you very much about its behavior. It just tells us as much as we need to know in order to apply it. And our first application is going to be proving that the language L accept is semi-decidable. But just the theorem itself misses a lot of the interesting features and nuances that you get into if you actually try to define the universal machine yourself. So, as I always say, there are more details in the notes than in the lectures. In this case, there are not that many details in the notes, but it is really a fun exercise, as I keep on saying, to try for yourself to think about how the universal Turing machine works and try to think about how you would actually write the Turing machine that does it. Anyway, we'll see the level of detail that we want to get into in the lecture now. So I'll start with the theorem. Maybe I call it. Let's call it the universal Turing machine theorem. And simply says there exists a universal Turing machine which we'll call U because it's universal. So our universal Turing machine is going to be defined over a particular tape alphabet. So the tape alphabet is going to be our universal tape alphabet, our universal alphabet. This won't do as the tape alphabet, why not? We can't just use this as the tape alphabet. What's missing?
The blanks.
Okay, this doesn't have a blank, so the tape alphabet is blank, needs to have a blank. Could potentially have some other things as well. So this is union. Could potentially have some other things, but we don't need it to, so we're just going to restrict to that alphabet. That enjoys following behavior. Behavior is that if we run on input strings of a certain form, say string means the same as word. So input string of the form encoding in a Turing machine with bullet followed by the encoding of an input word. Then the resulting execution of U on that input satisfies following 3 points. It terminates in some control state, we won't say what, it doesn't matter, just some control state. If and only if N terminates input W, it accepts if and only if N accepts W and it rejects only if N rejects. And that's it. It's universal in the sense that it's able to simulate the behavior of any Turing machine. If you've got a Turing machine M and you want it to simulate the behavior of M, well, you give it M as an input, and you want to simulate the Turing machine of M on whatever input you're giving the Turing machine M. So you give it, when I say give it M as an input, you give it the word encoding M as an input, and you give it the word coding the input of M, which is the second part of the input. And then by the theorem, the eventual behavior of the universal Turing machine on this input agrees with the eventual long-term behavior of the original Turing machine M on the original input W. Now, the theorem does not say very much in the sense that there's a much closer relationship between the behavior of the universal machine and the behavior of M on W than this theorem says. This theorem just says the end results are correct. But actually, the way the universal machine works is it's going to simulate the execution of M on W step by step. And just like when we were simulating a multi-tape machine by a single tape machine, it's going to necessarily work in such a way that one step of execution here is going to be simulated by many steps of execution here. Yeah.
I have two questions. The first one is, does this work for an arbitrary alphabet? Over some tape alphabet, sigma.
So this is sigma U.
Yes, yes.
So I'm restricting the alphabet.
Okay, but
Okay. But any Turing machine, but for the Turing machine M, we're not restricted to an alphabet because any Turing machine with whatever large alphabet, we're encoding using this alphabet sigma U. So these Turing machines M, their alphabet's not restricted. But this Turing machine U is a single Turing machine, so it's just defined over one alphabet.
Probably as long as you produce an encoding for M and W for arbitrary alphabet and also take another alphabet, right?
Yeah, I mean, we need to, the alphabet here needs to be the alphabet that we use on the encoding for M and W, but we're taking this alphabet because that's the alphabet we use. But if we'd been more economical at the start and just use the alphabet with 0 and 1, which we could have done, then one could also encode this over the binary alphabet. Yeah, you have two questions.
Yeah, the second question is, can we look up a concrete universal Turing machine and roughly how many transition does it have? So just
yes, you can use Google. But it will be, I mean, there isn't just one universal Turing machine because everyone that presents a universal Turing machine designs their own. And what I presented in the notes was just what I wrote. It wasn't based on any source material, so you won't find mine anywhere in the literature. But there's plenty of literature that involves universal Turing machines, and plenty of people have done computer science projects in which they produced a universal Turing machine, I think. Anyway, enjoy finding out. But I think it's the sort of thing that's fun to think about for yourself. Right. One other thing to say is, this is a beautiful result in the 1930s, a machine that can simulate the whole family of these kinds of machines. Nowadays, it's not at all surprising because I said last week, a Turing machine is basically an algorithm, or we can think of it as a computer program. It's both a computer together with an inbuilt program, essentially. And from a modern perspective, what we're doing is this universal Turing machine is like a compiler, or rather more an interpreter, one might say, for the Turing machines. So here you're writing your code, the programming language, together with you're writing your code, which is the Turing machine you want to run, and the input string you want to run it on. You submit it to your. I mean, I don't know whether the interpreter or compiler is the better. I think interpreter's the better analogy, submit it to the interpreter, and it will basically execute the machine you want. It's just a single machine that does this. But nowadays, kind of the analog of the universal Turing machine is a compiler for programming. Interpreter. Right, we're going to look a little bit at how one defines the universal Turing machine. We already have the encodings here, so we want to say how the universal Turing machine executes. So basically, you give it an input string, and that's the encoding of the Turing machine together with the encoding of an input word. And we want the execution of the universal machine to simulate the execution of that. So we want it to convert, the execution of this is going to be a sequence of configurations of the Turing machine M. And that execution, step by step, we want to translate into a sequence of executions of the universal Turing machine having been given that input. So the key idea is this, which I'm going to do with a picture. So let's move the camera. The key idea is a configuration of M. So we've got some so M is a single tape machine. We were encoding single tape machines. The configuration of M is going to involve its control state it's in, position tape head, and some portion of the tape, of the single tape that's not blank. So I'm going to call that, I mean, there might be some blanks in there, but everywhere outside this portion is blank. So I'm going to call this V. But the word, here we've got a V, which is the word over the tape of that of the Turing machine. And that's again V0 for the first. Let's suppose it's got K different elements, and the head position is going to be somewhere. We can always expand this so that it includes the head position. So we'll put this at, suppose the head position I. Okay. So when this gets converted to a configuration of U, in the execution of U. And for convenience, I'm going to use a 3-tape Turing machine for U. Okay. But we can obviously convert it back to a 1-tape machine using the ideas we had at the beginning. So for convenience, use a 3-tape U. The idea is on the 3 tapes, following information. The contents of the first tape are fixed, and we just put the encoding of the Turing machine M on the first tape. The point is we want to simulate M, so we're going to have to continually look up instructions in M to see what to do next. And it's just convenient to have that information stored nicely separately on a separate tape. So here we're going to have the encoding of the Turing machine M. And when we're simulating a configuration here, we nicely put the head at the beginning of the representation of M, the head for that tape. On the second tape, we're going to put the encoding of the state Q. Again, we'll put this will be quite a bit smaller than the encoding of the whole alone. Again, we'll put the head for this tape to its left. And here, we're going to put the encoding of the tape. So here we're going to have the encoding of this word the. But let's write it out. So the encoding of this word the, that's the encoding of the symbol V0, bullet, the encoding of V1, bullet, and so on. Bullet, some point we'll get to VI, which is the square that the head's pointing at, and so on up to the last symbol of the word here, and then that's where this heads, and all the bits. So basically, all the bits outside the interesting parts, these are all blank. So I'll put orange there to the, these bits are all blank. And where do you think we put the head on the third tape? Sorry? Yeah, we can put it in a dot before that. I think in the notes I put it here. I'm always putting things with the first character on, because actually if it was here, there wouldn't be a dot before it. So, but yeah, we want to pick up the head of this original machine at this configuration is here. And what do we do for the state? Well, so this is where there's a big difference between the simulation we had of a multi-tape machine by a single tape machine, where the states reflected, the state of the single tape machine reflected the state we were in the single tape, in the multi-tape machine. Now we don't need to do that because we've got the state encoded here. So in my notes, I call this snapshot. This particular state. And what this means is we're going to have a long execution here using lots of little steps, lots of which are doing like intermediate work in order to execute this machine. So one step here is going to be very, very many steps of the universal machine. But from time to time, we get back to the state snapshot. And the state snapshot means we've moved one step on from our previous. We've moved one step on in the original machine from our previous snapshot state. So we're now back in a snapshot of the original machine. You know, like a snapshot is an instantly taken photo at a point in time that captures that point in time. Okay, once we've got, we could not put any more information about the state into the state of the universal machine because the universal machine has to be universal. We've only got one finite set of states for the universal machine that has to work for all. No, so suppose we've got 50 states in the universal machine. We can still apply the universal machine to a machine M that has 1,000 states in it. So there's no way we can encode. We could possibly put the states of the machine M into it. Okay. So anyway, we use this one snapshot state to do it. And basically, the way the machine works. The way the machine U works is as follows. It's given its input, and it has an initial phase, which I call the setup phase. And in the initial phase, it takes the input, and it sets up the starting, it replicates this starting configuration. So basically, it takes the input, it writes the n part out on the first tape. It detects the length of the state, which it gets at the initial part of the encoding of the machine M, and it writes 0, 0, 0, however many times here to encode the starting state. And then it takes the word W and it puts that on the third tape, and it puts its head at the beginning of that because that's where the head starts at the start of the computation. And it starts in snapshot. So that's the setup state. Then it goes into the simulation state, which says, from such a position snapshot, proceed as follows. We look at the state we're currently looking at. We look at the symbol we're currently looking at. We then scan the Turing machine M for the instruction, if one exists, that matches that symbol and that state and symbol. If no such one exists, then we'll go into the termination phase. But at the moment, suppose one does exist, then that instruction tells us what to replace this with, how to move this tape head. There are three things, aren't there? State, what to replace the state with, what to replace the symbol with, and how to move this state head here. We simply do those three things. We overwrite the state from the information we've got here. We overwrite this symbol, and we move the tape head to the right or left, potentially creating some space if we need to, by bringing in another encoding blank into this space. And then we return all the heads to the right places, and these two heads to the right places, and go back into the snapshot position. So that's the simulation step. At the time that we don't have an instruction that matches here, we go into the finishing phase. I don't actually quite remember what they call it in the notes, but anyway, the completion phase. And at that point, we read this state. If this state is accept, if this state is the encoding of accept, we go into our accept state here. If this state is the encoding of reject, we go into our reject phase, our reject, and otherwise we don't need to do that. Otherwise, we don't need to do anything. Okay? And that's how it works. So in the notes, these properties are summarized as three lemmas or propositions. I don't quite remember what I called them. One, the initialization proposition, which says how the universal machine simulates the initial part, the step-by-step part, the second one, and the final part for the third one. And those three results together combine to give us this theorem. Okay, yes?
You said that, if I understood you correctly, you said that in the initialization phase, the universal Turing machine writes the encoding of n onto the first state.
Yes.
Yes. From where?
Well, it's given that as its input. So this is when we run the universal machine on this input.
Okay.
Okay, so the universal machine, it doesn't say write n in its instructions, it says read my input, okay, parse it as the encoding of a Turing machine until I get to the end of the encoding of a Turing machine, which I detect because I have closed square brackets followed by bullet. That means I've got the end of the Turing machine. At that point, yeah.
Okay, but one more detail. This input is given on the first of the three tapes.
Okay, so for the 3-tape version, it doesn't matter. It can be.
Okay, yeah.
But really, this is the 3-tape version. Let's convert it to a single-tape version, and it's just given on the single tape. And then, in the end, I'm describing it as a 3-tape machine because that's easier. But in the end, it's a 1-tape machine.
So in my mind, this initialization phase with the 3-tape version is kind of, and the parsing is unnecessary because you have the information parsed already. You have the
well, no, because you still start off with this whole thing on 1-tape. Okay, so you have to detect the end of the machine, but it's detecting the end of the machine is a kind of trivial thing to do. Although you might actually detect whether it's a well-formed machine, and that would require quite a bit of computation. I think probably in the notes I start off by detecting whether this is indeed an encoding machine. That would be a good thing to do. But I think that's enough details. And as I say, it's good that you're asking questions because it is a fun thing to think about for yourself. So now you've got this, try and define your own universal machine, and then run it on the Turing machine simulator if you're going to use an exercise part. That would be a big challenge to do that. Anyway, let's move on. So having done this, so this is all I want to say for the universal machine. Let's keep the theorem and clear the right-hand board. And what we want to do is use this to prove the semi-decidability of L except. So, theorem, second theorem of today, oh no, the third, obviously existing to be Turing machine, the universal Turing machine. Third theorem, L except is semi-decidable. And this is now almost easy. In fact, maybe I'll write the proof as if it were easy, and then I'll ask if anyone can spot what's missing. So we simply construct a Turing machine. We're going to, it's again one of these proofs, which is we use the Turing machine U to define the Turing machine we need. And the Turing machine we need is the Turing machine that accepts, the Turing machine that decides the language L accept. So we construct, using U, we're going to construct a machine, a Turing machine S, that does the following. Yeah, I was going to try to leave it as I present the easy part and then ask what's missing, but it's actually very hard to see how to do that. So I'm afraid I have to give the game away at the start and start off with the tricky stuff we need to do. So this is a Turing machine S, it takes some input word, and the first tricky thing it needs to do is it reads, S reads its input word. So we're trying to decide the language L accept, which is over the alphabet sigma U. So this is a word V over sigma U. And it checks if V is of the form M bullet W, meaning it's divided into two parts separated by a bullet, where the left part is the encoding of the Turing machine and the right part is the encoding of a word. So this is some semi-serious parsing going on here. It's parsing the input to see if it looks like the kind of word that might be in the alphabet. Sorry, word in the language I'll accept.
All the form here means what? Like how deep do you go to? Does it like
so we're
just
going
check
to
if there's a bullet?
yeah, for some T M M. Let me just finish the sentence and input word W. So what this means precisely is this initial part is going to decide either yes or no. Does there exist a Turing machine M and a word W such that the input is of this form, such that the input equals the encoding of M bullet the encoding of W. Okay. Now that's not that's not that difficult, because to be this, it needs to start with a sequence of zeros and ones of a certain length, which is the encoding of the, I don't remember whether I started with the state or the word or the symbol, but anyway, it's the encoding of one of those. Bullet and a sequence of zeros, zeros, ones, and minus ones. So it's a sequence of zeros, ones, and minus ones, followed giving a length, followed by a bullet, followed by a sequence of zeros, ones, and minus ones, giving the next piece of such information. After which there needs to be a finite number of things in square brackets, or sequence of things in square brackets, each of which consists of a pair of things separated on the left by a bullet, and a triple of things separated, sorry, a pair of things separated on the bullet on the left of the double bar, and a triple of things on the right of the double bar, again separated by bullets. Each of those things need to be of the appropriate lengths to match the initial data. Moreover, we're talking about deterministic machines. The transition is a partial function, so you should never get any conflicting instructions telling you to do two different things on the same information of a state and symbol pair. After that, you need to get a bullet, and then you get an encoding of a word, which is an easy thing. So this is non-trivial, but it's perfectly computational. I've kind of basically described how to do it. So I think the right word for this is that it's fiddly. But it can be done. So if V is not of that form, well then this word V cannot be in the language I accept, so I simply reject. So if V is not of this form, if V not of the above form, let's reject. And then if V is of this form, well, in that case, we want our machine S to accept this word if and only if N accepts W. But by the simulation property of the universal machine, that holds if and only if we can simply just run the universal machine on the input word V. So otherwise, we run U on V and go into whatever state it ends and end in the end state of U. At this point, in order to, this is a U looks like a V, but anyway, V looks like a U. At this point, V is of the form encoding around bullet W, and running U on it will accept if and only if M accepts W. In other words, if and only if the word V belongs to the language L accepts. Okay. And this initial part is perhaps necessary only because I maybe don't give enough information in this theorem here about the universal machine. I needed to give me this theorem about the universal machine. I needed to put this in just in case the universal machine might accidentally, if given some ill-formatted input, it might accidentally accept it. Hence how we define the universal machine. But an alternative to doing this initial part here would be to maybe define the universal machine in a more careful way to explain exactly what it's doing, and that part could be put into the universal machine instead. Okay? But somewhere along the line, you need to make sure you're not accepting ill-formed input strings that are not of the relevant form. Okay, so we're done. That shows that the language is semi-decidable but not decidable. It's kind of intuitive because we're trying to test whether a machine accepts the word W. So running the machine results in accept. It's kind of not surprising that we can give positive information for that if it happens, because we can basically run the machine and see it happen. But then undecidability means we can't say for sure if it's not going to happen, because we're running a machine and we don't know, it might just be that we haven't run it for long enough. We never know if the machine M just hasn't accepted W up to this point, or is not, we don't know it's not going to accept in the future. And basically the undecidability part earlier says there is no clever way of building an automatic procedure that will detect when that happens. Okay, so just want to mention one other thing from here. So this is a particular language. We've got a language that's undecidable but semi-decidable. there's a more famous version of this language, and that's due to Turing, and is in sort of popular culture. And this is called the halting problem. And essentially, the halting problem relates to the discussion I just had about why semidecidability is not so surprising, and the difficulties that one has with decidability. And the halting problem so informally, the problem as is relevant to computer science, if you like, and to the real world is we cannot decide given a computer program, where decide means automatically decide by some algorithm, given a computer program and input to the program, whether program halts on that's it, or whether the program simply runs forever. And this is relevant to the real world because there's a common source of errors in computer software, probably the sort of thing we've all encountered. That so some mistake in some professional software or something, you do something and the program just goes into some infinite computation and your computer hangs, and you have to abort the thing, and it wasn't intended to do that. So that's an error in the program. The relevance of this, there's no algorithmic way of deciding whether or not this happens. That's basically what this says. To the real world is that this tells us there's a mathematical reason for it being very difficult for programmers to be able to tell whether or not their programs have this sort of bug. Because there's no algorithmic way of just giving a program saying, okay, let's test it to see whether or let's find a way of testing whether or not it has these unique bugs or not. So this is a source of difficulty in the real world, and it's nice that there's a mathematical theorem that underpins it. And for us, then, this is basically the truth of the state of the world. We have to live with this. But for us, then, we're going to have a precise formal version of this to do with Turing machines, because Turing machines are our model of computation. So that's the informal version. So our formal version is we're going to define another language, L-halt, which is very like L-accept, only just a little bit different. So we want to detect for a program and its input. So a program for us is a Turing machine. The input is the input on the tape. So it's going to consist of pairs of Turing machine followed by a word. And instead of now saying does accept W, we're simply going to say is those pairs where M is Turing machine, a word. I'm being a bit informal, but the same restrictions here as before, but instead of accepts W, we simply say halts on input W. So we're testing halting. So M rejecting W would also count as halting, as it didn't count before. And the theorem is that L halt is again semi-decidable it is undecidable. So that's not decidable. And as an exercise, you might think how to prove this. You can either prove it directly from the universal machine, like we were doing before, or better, you can try to deduce it as a consequence of the theorem that L accept is undecidable and L accept is semi-decidable. That's an alternative proof. And some other exercises along similar lines are going to be done in next week's exercise class. Not precisely this one, but try to do this for yourself. And then you can see in next week's exercise class whether you're kind of doing things along the right lines. Okay, so I think that's everything for today. Questions? Yes, Karen?
At least we have termination results for well-packed programs and simple-packed lambda calculus, right?
Yes.
At least those terminates.
Okay. All right. So there's a problem with programming languages that are sufficiently expressive that you can do things like while loops and recursion and things like this. In those kind of languages, you have this problem that you can't tell if a program terminates. But there are some restricted languages, like one source of such languages is something called type theory, that are defined in such a way that all the programs you can write automatically terminate. In which case, you don't have problems like this which arise, you have a different problem, which is how to write interesting programs which are useful for people to do things with. Other questions? Okay, good. Well, that's it for today then. See you next week.